Hello, and welcome back to my YouTube channel. My name is Professor Govala, and today we're going to be doing the fourth installment for EE 220. And today we're going to be talking about Ohm's Law, Kirchhoff Current Law, or KCL, and Kirchhoff's Voltage Law. And these laws are the fundamental or building block laws for any electrical engineer. To begin, we're going to first define what's known as conductivity, where its symbol is sigma, and conductivity of a material is a measure of how easily electrons can drift through the material. It's a measure of how electrons can drift through the material when an electron voltage is applied. Is applied across it. And the units of conductivity are called Siemens per meter, or S over M is equals to sigma. Next, we're going to define resistivity. And this symbol is rho, and it's the inverse of conductivity. Rho is the inverse of conductivity. Or rho is equals to 1 over sigma. And just to be clear, we have Simon, which is S, which is equals to 1 over an ohm. We have conductivity, which is sigma, which is equals to Siemens over meters, or 1 over ohm times meters. And we have resistivity, which is rho, which is equals to 1 over rho, which is equals to ohms times meters. Some material classifications are, so for conductors, we want something that can easily attract electrons. So these are primarily metals. You also have something called a semiconductor, which is mainly things like silicon and germanium. And these are doped, either P-type or N-type. And then you have dielectric. Dielectric, which are also called insulators. And essentially, if you have a diagram where you take a metal and you cut it on both ends, given a certain length of that metal, L, the conductivity of that metal, which is specified, and the area of that metal, of the cross-sectional or the end of that metal, you can find the resistance to be L over your conductivity times your area. So essentially, you're multiplying your conductivity by a frame A, and then since conductivity is the inverse of resistivity, you put 1 over that, and then you multiply it by a length L to get the full length of your resistance. There are a few types of resistors. Specifically, some types of resistors you may see are rotatable resistors, and these are shaft potentiometers. And you may have heard of these, but what they look like is something like this. Where you have a resistive material around this shaft-like area. So this in red is a resistive material, like carbon. And you have a rotator, and this is kind of how your radio knobs work in your car. And you have a 3-terminal. This is 1, this is 2, and this is 3. You have a 3-terminal potentiometer. And we also have just a screw top potentiometer, and these are normally 2-terminal. A screw top potentiometer. And then you also have a tubular shaped resistor. And how this looks is a tubular. So this is a tubular shaped resistor, and essentially it's split into a couple of lines, specifically 6 lines, 3, 4, 5, 6, where depending on a table, you can look this up on a table, a resistive table, these have values. And this is the amount that you multiply, the 10th position. So for example, if it's K, you multiply this values by 10 to the 3rd. And then this is the percent range. So if you have plus 1%, it's this value plus or minus 1%. And you have the temperature rating. So ppm is parts per millions over degrees Celsius. This just means that if you change the resistor value by 1 Celsius, you change the resistor value by 5 times 10 to the negative 6. So these are kind of the meanings of those colors on your tubular shaped resistors. And now a screw top potentiometer looks something like this. And these are normally used when you have a stationary resistor. So you have 1, 2, and 3. And this dial, this tubular, this screw top here can either go up or down. It can go up or down by a resistance R13 or R23. And essentially it has an R max that goes from here to here. So this is a screw top potentiometer, and this is a tabular shaped resistor. I hope these make sense. These are 3-terminal devices, and this is a 2-terminal device. So some common resistors you might find in industry are what are called thermistors. So they measure temperature. Piezoresistive resistors. So these are like strain gauges or pressure sensors. They're resistive to pressure. So again, this is temperature. Resistive to temperature. This is resistive to pressure. There's another one called a light dependent resistor, or an LDR, and these are resistive to light. So when you walk into a room and it gets the light gets darker, this can pick it up, and we can then say someone's in the room and turn on the lights in that room. We also have a rheostat, which is a two-terminal. Any rheostat is a two-terminal variable resistor, like the tubular resistor we talked about, and a potentiometer. Which is a three-terminal resistor. Terminal variable resistor. And we'll see more of these as we go on, but I hope this makes sense in terms of resistors. We use resistors a lot in electrical engineering, and especially in schematic drawings and to prove different points. So we spend a good chunk of time defining them and giving examples so that in the future we know what we talk about when we talk about resistors. And next we talk about what's called the IV characteristics of an ideal resistor. And in order to do that, we need to first talk about Ohm's law and who created Ohm's law. So there was a German physicist named George Simon Ohm. George Simon Ohm, which we have to give credit to. He's the creator of Ohm's law, and as a result, we named the law after his last name. And he said that the voltage V across a resistor is directly proportional to the current I flowing through it. Again, so he said the voltage V here across a resistor is directly proportional to the current I flowing through it. And how we define that is if you have a resistor R plus minus, remember voltage, we talked about voltage is just the voltage difference. So there's a voltage VA here and a voltage VB here, and there's a current I flowing through it. We could say that VAB is equals to VA minus VB. As a result, I is equals to VAVB over R, which is also, this is just equals to VAB over R. So Ohm's law can be written as VAB is equals to I times R, or I is equals to VAB over R. So there's two ways to write that. And we want to define the current and voltages through an ideal resistor. And through a real resistor. Remember, we're dealing with, sometimes in an analysis, the ideal resistor comes into play because the difference in our values, if we consider ideal versus real, is insignificant, and the ideal situation leads to an easier analysis method. As a result, if we don't lose too much value when using the ideal situation versus the real situation, we might as well use that for analysis because it's easier to do. So what an ideal resistor looks like, the IV curve. So this is voltage, this is current. It looks like this, where R is the slope. And if we say that for this R is equals to 0.5 K, we might get for a 1 volt voltage, we might get 2 milliamps for our current. And then as we get lower, we could see that our resistor value needs to increase. So 1 K ohm will lead to a 1 milliamp current. And in this situation, all the way down here, this would mean that our resistance R is equals to infinity. And when resistance is infinity, this is basically an open circuit. And if you don't remember what an open circuit is, please check out my last video to see the definition of that. And as you go up in this depiction, you will see that if R is equals to 0 at this line right here, so R is equals to 0, and this is a closed circuit, and no voltage is 0 in this situation, and in this situation over here in blue, current I is 0. No current passes through a open circuit, and no current passes through a closed, or sometimes called a short circuit. This is a short circuit. Again, check out my last video if you don't remember those concepts. And for a real resistor, what it actually looks like, and I'll just draw the first case in red here, in black here, is something like this. It's linear, and then it curves up. It saturates at a certain point. It saturates at a certain point. And this is the maximum current that can pass through it, and this is the minimum current that can pass through it, where, again, this is V and I, and we refer to this as the linear region. And we always want to be functioning in the linear region when we're dealing with resistors. We want to now talk about the main point of why we want these currents to flow through a resistor. And to do that, we introduce power. And it says that the flow of current in a resistor leads to power dissipation in the form of heat or heat and light. And that's essentially what we want, especially like in the terms of a light bulb. When you pass current through it, it releases what are called photons, and those photons vibrate at a frequency that can be picked up by our eyes and allow us to see other things around on a high level, on a very high level. And it also releases in terms of heat because the light bulb gets hot because the electrons are excited. Also, if you have an electric stove, that's the heat that is used to cook your food. But then also you can see that light is emitted in terms of the red light that are around the rings of your electric stove. And essentially, we defined power in the last video, and you can check that out to see how we saw P is equals to I times V. But we also want to generate some other equations for P in terms of just I and R and V and R. So we know I is equals to we know V is equals to I times R, so we can replace V with IR, and we get I squared over R. And we also know that I is V over R, so we can replace I with V over R times V, which is equals to V squared over R. So in general, we can talk about and say that P is equals to I squared R or V squared over R. So this power equation, from the help of Ohm's law, allows us to be able to solve for power given just the current through it and the resistance through the resistor and the voltage through the resistor and the resistance of the resistor to find power through the resistor. So it's very, very important. This equation is extremely important for electrical engineers. So now I'm going to do two examples, and what I'll do is I'll write out the example on this screen and solve that example. So here's the question that we have, the first example we have. Essentially, you have this battery, this 12-volt battery right here, that is being attached to a motor, which has a resistance of 2 ohms. And essentially, the reason why this resistance is so low for a motor is because we want a lot of current flowing through here, right? If we have a low resistor, we have a high current. And the reason why we want a high current is because we want a nice big magnetic field so that the motor can spin, especially if you have industry-like motors. But that's a different topic, which we will talk about in later chapters when dealing with inductors. Now, we have this wire, which is 6 meters long on both the top and on the bottom. And we have to realize that wires also have a resistance associated with them, right? They pull current as well. And the voltage here is not the same as the voltage here. As a result of that, this wire is actually taking a little bit of this 12 ohm volt battery that we're supplying it. Now, it's not a lot, but it still should be considered when doing analysis. So the first question says, find the resistance of the wire given that the total wire is 12 meters. And for copper, we're using a copper wire in this case, our resistivity is 1.72 times 10 to the negative 18 ohms per meter. And the area, which is given by this AWG10, has a diameter of 2.6 millimeters. Now, the second part of the question is asking for the fraction distributed by the battery that gets delivered to the motor, the fraction of power. So the wires are actually taking some power, and also the motor is taking some power, but how much is being delivered to the motor is the base of the question. So I hope you understand the question. So we'll dive into a solution for A. And first, what we want to do is use a trusted equation that we learned earlier, which says that RC will be equals to rho L over A, which is 1.72 times 10 to the negative 18 times 12 over, again, this is the length of the resistor, the L, the entire wire, sorry. This is the length of the entire wire, which is 12. And then pi, because it's the area, times, if you divide 2.6 by 2, you get 1.3 times 10 to the negative 3, because it's millimeters, squared. And all that is equated to 0.04 ohms, or 40 milliohms. And that's your answer for A, right? Normally we use just ohms, so 0.04 ohms. You will never really see milliohms being used, but that's just a convention thing. So now B, we can first see that the total resistance, R total, is equals to R wire plus RC. Excuse me. This is R wire plus RM, or the motor resistance, which is equals to 0.04 ohms plus 2, which is equals to 2.04 ohms. Now, we can then calculate our I, which is equals to V over R. So we're given a 12 volt battery, and our resistance is 2.04 ohms. So this is equals to 5.88 amps. And we know that this is equals to that because based on the conservation of charge, we know that the current through a loop is the same. So this is all, so the current through the wire and the current through the resistor is equated to I. Now we can find the power delivered using what we've learned in the past, IV, which is equals to 5.88 amps times 12 volts, which is equals to 70.56 watts. And the motor the power delivered to the motor is I squared times that R, which is equals to 5.88 squared times 2 ohms, which is equals to 69.15 watts. So the fraction of the power delivered to the load or the motor, so fraction is PM or P motor over P delivered, which is equals to 69.15 over 70.56, which is equals to 0.98 or 98%. Essentially, only 2% of our power is dissipated to the cable, which is really good. But again, we can maybe use different techniques, and this is what power systems engineers do, is use different techniques to try and minimize the power loss in our wire from 2% to 1% to 0.5%. So for the second example, again, I'm going to draw it out. So this is the second question we have, example 2. We're given this circuit diagram where we notice that this is a sinusoidal voltage source, and we're given a R1, R2, and R3 all in parallel because they have they share the same node at the top, and they have extraordinary nodes, which if you don't know what those are, again, check out my first video. And we're tasked to find V1 through V6. So in order to find V1, V2, and V3, we notice that it's in the same node as my voltage source. As a result, this voltage source is equated to V1, V2, and V3. Where, again, just for a little bit of knowledge here, this 377 has to equate to 2 pi times a frequency. As a result, this cosine function is getting put in at a 60 hertz frequency. And now, in order to find my voltage V6, V5, and V4, we notice that this is also just grounded. So essentially, V6, V5, and V4 are equals to 0. And this is equals to Vs. So again, this problem, the first part, A, was a bit easier, but it's important to notice that this node here is the same node. As a result, this is just my drop, and this node here is the same node, so this is just my ground. Now, the next part of the problem, we're tasked with finding the current supplied by the source of the 3 loads. So finding IS. So B says find IS. In order to do that, we notice that I1 is equals to V1 minus V6 over R1, or this is equals to 170 cosine 377t over 1k, or 10 to the third, which is equals to 0.17 cosine 377t amps. And again, we should notice that V6 is just equated to 0. So as a result, that's why we only just take V1, and V1 is our trusted 170 cosine 377t. And to keep going, I2 will just be V2 minus V5 over R2, and I3 is equals to V3 minus V5 over R3. This is equals to 170 cosine 377t over 500. This is equals to 170 cosine 377t over 250. This is equals to 0.34 cosine 377t amps, and this is equals to 0.68 cosine 377t amps. As a result, we can say that I supplied, I of t supplied is equated to I1 plus I2 plus I3, which is equals to 1.19 cosine 377t amps. And if you don't understand why we can say that, this is a quick depiction. The current coming in here gets distributed here, here, comes here, here, and goes down here. But at the end of the day, it comes back. So this IS comes back. So IS is equated to I1, I2, plus I3, all coming back to ground. That's where we get this equation from. So I hope that makes sense. With that being said, let's dive into Kirchhoff current law. And you will use this for the remainder of your electrical engineering careers. So it's very, very important to know how it's defined and what it is. So I'm going to define it now. So this is the law. It says that by the law of conservation of charge, a node cannot store, generate, or consume energy. Therefore, the algebraic sum of the currents entering a node must always be zero. And this means that at any node n, the sums coming in n is equals to 1 through n of the currents must equate to zero. And a simple example of that is if you have a node and you have wires sticking out of that node and the currents are coming in, so I4, I3, I2, and I1, where this is a plus, a minus, and a minus, we can say that if I1 and I4 are entering, then I2 and I3 are leaving, then I1 plus I4 minus I2 minus I3 is equals to 0. You can also switch it and say that I2 and I3 are entering and I4 and I1 are leaving. As a result, you get negative I1 minus I4 plus I2 plus I3 is equals to 0. And essentially, you could say that the total current entering must equal the total current leaving, or just I1 plus I4 is equals to I2 plus I3. If you use this equation, which some individuals use, or you can use this equations which some individuals use, you still get to this equation. And this is Kirchhoff current's law. If in any situation you have a current I and you get a negative number, this just means that the current that you guessed, the real current actually is going the opposite direction. So if you ever get a negative current, that just means that your guess you made was wrong and it's actually going in the negative direction, in the opposite direction. So that's just a quick note to make. Now let's take a quick example to show this in concept. So if we have this as our example where we have 5 nodes, node 1, 2, 3, and 4, and 5. And we have these resistors on the connecting points of the nodes with a voltage source and current sources integrated within them. We can write different nodes. We can write things about the nodes. Specifically for node 1, we can write a KCL, which says that minus I1, because it's leaving, I1 is leaving the node, minus I3, because again, I3 is leaving, plus I5, because I5 is entering, is equals to 0. This is, let me fix this. This is at node 1. This is at node 2. Again, this says that I1, so I1 is entering the node. I1 is entering node 2, so it's positive I1, minus I2 because it's leaving, plus 2 amps because 2 amps is entering, is equals to 0. Again, at node 3, you have minus I2 because I2 is leaving, or minus 2 because 2 is leaving, minus I4 because I4 is leaving, and plus I6 because I6 is entering, is equals to 0. And then at node 4, we have a minus 5 because the 5 amps is leaving, minus I5 because I5 again is leaving right here, and minus I6 because again I6 is leaving, is equals to 0. And then last but not least, at node 5, we have I3 is entering, so I3 plus I4 because I4 is entering, plus I2 because I2 is entering, and plus 5 because 5 amps is entering, is equals to 0. As you can see, KCL, or the law of conservation of charge, is met by these equations. And essentially, this is very, very important in terms of dealing with nodes. We need to be able to recognize and label these currents when we're doing analysis using KCLs. Lastly, we're going to talk about Kirchhoff's voltage law. So Kirchhoff's voltage law, or KVL. And essentially, we're going to define it first. And essentially, KVL states that the law of conservation of energy says if we move an electric charge around a closed loop starting and ending at exactly the same location, the net gain or loss of energy must be 0. And since voltage is a surrogate of energy, the algebraic sum of the voltage around a closed loop must always be 0. So if you have voltage drops Vn around a closed loop from n is equals to 1 to n, all those drops must equate to 0. And an example of this is, for example, given a circuit like this, where you have the following sign conventions for the voltages, and you have 4 volts here and 6 volts here, in KVL, you want to go around the loop like so and write voltage equations. The way I do it, and most people do it, is if the current is coming in this negative sign here at 4 volts, I put a minus 4 volts. If the current is coming in at this plus sign here for the resistor, I put a plus V1. Here it's coming in the minus terminal for V2, so I put a minus V2. And then here it's coming in the minus sign for 6 volts, so I put a minus 6 volts. And here it's plus for V3, so I put a plus V3. And here it's a minus V4 for R4. I forgot to label that, R4, R2. So I put a minus V4. Some other textbooks may use the sign convention of it exiting, and we'll do that next just to show that it's the same thing. So now, if I continue with this, I get that, this is all equated to 0 per our trusted KVL proof or law. And it says that 4 plus V2, so 4 plus V2 plus 6 plus V4 is equated to V1 plus V3. V1 plus V3. Now, if I were to do it by the convention of if the current is leaving, I use that sign. This would be plus 4 volts minus V1 plus V2 plus 6 volts minus V3 plus V4 is equals to 0. And you will see that you would get 4 volts plus V2 plus 6 volts, V2 6 volts plus V4 is equals to V1 plus V3. So essentially, depending on what you want to choose to do, you get the same results. For the remainder of this lecture series, I will be using this convention where depending on what the current enters in, so in this case, minus 4 volts plus V1 minus V2 and so on, where the current is entering is the sign convention that I will use for this lecture series. And essentially this means that this says is that the total voltage rise, because in this situation, if I go from a minus to a plus, if my current is going from a minus to a plus, I'm rising in voltage. And if my current is going from a minus, if my current is going from a plus to a minus, I have a voltage drop. And in this situation, it's saying that total voltage rise is equals to total voltage drop, which is equivalent to my trusted law. We will then finish it off with a quick example. And this is the following example that we want to solve, and it's asking us to find the value of current I in the circuit. And normally, if I'm given a circuit like this, I consider that the only source that has a voltage rise is my battery in terms of my current convention, being that it's going in this direction. So this is a voltage rise, and the remainder of the resistors are voltage drops. So they go from plus to minus, like so. So that's the first thing I do, is I consider that the resistors are pulling in a voltage drop. And I label this as V1, V2, and V3, where when I write my KVLs, I could say that minus 12 volts plus V1 plus V2 plus V3, which is equals to minus 12 volts plus 10, which is the resistor, times I, which is a current, plus 20 times I plus 30 times I is equals to 0. Again, this is 60 times I is equals to 12. And that means that I is equals to 12 over 60, which is equals to 0.2 amps. So the current flowing through this loop, I, is equals to 0.2 amps. In my next video, I would do a more extensive example of both KCL and KVL. And essentially in this lecture, we talked about these two concepts, we introduced them, and we also talked about Ohm's law, and we talked about resistors. So I hope this all makes sense. Again, if you're feeling a little bit lost, please check out my last 3 videos. They do a really good job of explaining everything up to this point. Lecture 1, Lecture 2, and Lecture 3. And please don't forget to like, share, subscribe, and comment if you have any follow-up questions. Thank you, and bye.